Hi, my name's Rick Bacon. I'm Chief Executive of Aquametrology Systems, and I'm joined today by Dr. Vladimir Dozortsev, who's the inventor of an innovative approach to treating a wide range of contaminants found in drinking water and wastewater. Vlad and I have been giving presentations to water treatment companies, industrial companies, on the benefits of this innovation. And out of that have come a range of technical questions that we felt it was worthwhile addressing separately because they're common to many of the presentations that we've been giving. So, hi there, Vlad. One of the first questions was, how does this treatment system work in the case of removing phosphate? Phosphate being a major contaminant that is prejudicial to surface water resources. So could you talk us through a bit about the process itself?
Absolutely. Thank you, Rick, for inviting me. So Safeguard H2O proprietary treatment approach is based on well-studied and long-known laws of electrolysis. Our electrolytic system produces ferrous reagent in situ on demand based on very intensive electrolytic process during which sacrificial iron anode dissolves in water, producing highly concentrated ferrous reagent, which can further be injected into treatment process and react with phosphate molecules, bind them, and precipitate. So this is, in short words, principle of our approach.
Great. Well, that's really helpful. So there are a number of treatment systems, technologies that have been around for almost ever. One of the alternative systems to ours is referred to as electrocoagulation. And sometimes confusion arises between what we do and the approach of electrocoagulation. So maybe, again, you could sort of draw a distinction between the two.
Yes, totally. So basically, electrocoagulation process and our approach conceptually similar. Both approaches utilizes electrolysis law. However, there are several very important differences. First and most important difference between electrocoagulation process is in electrocoagulation, entire water flow which should be treated passes treatment system. In other words, electrocoagulation module serves as a dosing module for the reagent, ferrous reagent, and at the same time it serves as a contactor to react reagent, ferrous reagent with phosphate, coagulate it, and remove. This difference actually causes a lot of problems, potential problems for electrocoagulation, because first you need to adjust parameters of water coming into coagulation model oftentimes, such as pH or conductivity, and then you need to use a lot of reagents for adjusting those parameters. But most importantly, colloids produced during electrocoagulation process, basically ferric hydroxide colloids, may precipitate on the electrode surfaces and follow them. In this case, electrodes become what people call in industry passivated and stop serving their main purpose, producing reagent of demand. And those passivated electrodes eventually fail and have to be removed and replaced or treated, which makes this process inefficient and costly. Another problem with electrocoagulation actually relates to passivated electrodes from other side, in which passivated electrodes start generating side byproducts, organic and inorganic, which can be highly toxic and cannot be discharged. Also, the passivated electrodes, of course, consume much more electricity, which increases the resistivity of the system and consume more electricity, which increases costs. And finally, electrolytic process in electrocoagulation is very bulky, having very big footprint and have problems to scale. It's sometimes impossible to scale it down or up. And in this case, design and implementation of electrocoagulation modules may be problematic for certain field conditions.
Thanks, Vlad. That's a really helpful insight into some of the challenges of using electrocoagulation. It'll be really helpful, I think, to then look at it from the other side, which is in terms of deploying the Safeguard H2O system, what are the advantages of that? What benefits does it bring to the end user?
Thanks, Rick. Key advantage of Safeguard H2O is in its design and approach, where ferrous reagent produced in highly intensive manner within very small and compact electrolytic device, which produces highly concentrated reagent, up to thousands times more concentrated than electrocoagulation system. Then this reagent, freshly produced reagent, can be injected into the treatment flow or bulk and react with phosphorus and accomplish removal. The advantage of this approach is based on the fact that controllability of this module is much higher. We can maintain very favorable and comfortable conditions for electrolysis, during which generation efficiency of reagent is nearly 100%, and electrode health maintained by proprietary hardware and software, and electrode conditions can be monitored. So this compact and flexible electrolytic device can be easily integrated and scaled, and of course approach is modular, which allows to virtually treat a system of any size.
Great, that's very helpful, thank you. So another question we've been asked on several occasions, Vlad, is how autonomous is this system? Because many utilities are faced by the challenge of they're using bulk chemicals or planning to use bulk chemicals. These are very toxic and hazardous. They require storage and frequently truckloads delivered every day or every week, which requires manpower and handling and everything. So can you talk a bit to the how much autonomous availability this system can offer?
A good question. Autonomy comes from two aspects. One is automation of the system and the ability to run independently. And second is coming from load of iron precursor, capacity of iron anodes or electrodes within the module itself. So automation of our system is very high. It's practically completely unattended unit, which can run using our proprietary software and controlled by process operator remotely. It sends health status and electrode usage in real time, and basically warns operator when electrodes coming to exhaustion and need to be replaced. The load of electrodes, it's also may be very flexible depending on process and site needs. In certain sites, they have available personnel daily, and they will be interested to replace electrodes frequently. On some sites, unattended remote sites, the load should be higher to be able to run a module up to 2 weeks time periods. And we obviously can provide specific or customized module based on needs.
Thank you, that's really helpful. So another very important question is the utilization rate of these iron anodes. So could you answer that concern?
Yes, it's very important concern because anode or metal load anode utilization rate tied to efficiency and controllability of the process. In case of Safeguard H2O, based on unique features of this design and control, we can utilize electrodes practically 100% without any risk of passivating or following the electrodes. And it allows first to run process in very stable and controllable manner and save money on precursor.
Right. So another challenge for water treatment plants that are trying to deal with phosphate is that they've got, on the one hand, variable levels of phosphate they have to remove, and at the same time, they've got to achieve a regulatory limit in their effluent for the presence of that phosphate. So in that very dynamic situation, how do you ensure that the treatment system, there's enough reagent, not too much reagent, to deliver against that regulatory limit and ensure compliance?
Yes, it's very important and maybe even key process control question. Phosphorus removal is a reaction based on stoichiometry. And first thing to answer here is to monitor incoming levels of contaminant, in this case phosphate. And aquametrology systems has all the capabilities to provide frequent influent and effluent monitoring on both phosphate and iron. So first thing what we will do, we will monitor incoming phosphate levels. And based on this, we will adjust our dose, reagent dose, which will be sufficient to treat this amount of phosphate. Also, we will monitor settling tank where contactor or settling tank where reaction of interest occurs, and we will know dynamics of this reaction and degree of phosphate removal. And if needed, we can adjust, increase or decrease iron ferrous dose. And lastly, we can also monitor residuals of iron, which will ensure that we are not overdosing and wouldn't exceed iron MCL level in effluent.
Thank you. So following on from that, Vlad, one of the challenges is obviously producing a controlled dose, exactly what's required to treat for the amount of phosphate. And one of the challenges of the traditional treatment system based on electrocoagulation has actually been achieving that. And that derives from the need to maintain the electrodes in pristine condition. So can you talk to how your proprietary system addresses that challenge of anode electrode maintenance?
Very important questions. So in a Safeguard H2O system, we address electrode health situation in by multiple means. First, we track using our software the health of our electrodes continuously, and based on very high, nearly 100% reagent generation efficiency, we know how system performs. At the same time, we maintain very comfortable and optimal hydrodynamic conditions within our electrolytic device based on its compact and flow-through design. And by this, we can ensure that electrolytic conditions are favorable. And lastly, we have proprietary ultrasound-based approach for electrode regeneration, which we can turn on every time when system detects any form of reduction in electrode behavior. So by those means, we can ensure that our electrolytic device can run virtually unlimited time without any damage to electrodes and loss of the efficiency.
Thank you very much indeed. And so I think that's hopefully, for people watching this, a deep dive into some of the very technical aspects of this technology. You can't get away from that. But explaining how the Safeguard H2O system essentially incorporates the benefits of well-known chemistry for treating phosphates, but at the same time avoids the multiple disadvantages of traditional treatment system, either based on ferric chloride bulk chemicals, ferrous sulfate, or electrocoagulation, which has been tried and failed, and we've managed, I hopefully, explain why the limitations of both systems in that respect. So if anyone has any follow-up questions, they should contact myself or Vlad. We'd be delighted to address them. Thank you, Vlad, for your time. Much appreciated.
Thank you very much.